Hello and welcome to another tutorial in the mini-series on calculus at the higher level. And in today's tutorial I will be talking about the chain rule, which is a very important and useful technique in the calculus of differentiation. Because it's such a useful technique, I'm going to split this topic into two tutorials. So in this tutorial I will remind you about composite functions, because that's what the chain rule allows you to differentiate. We'll then go through a relatively simple, straightforward derivation of the chain rule, and I'll show you in action on a simple function so you can see how it works in detail. And then in the next tutorial we'll apply the chain rule to a number of different examples, and there you'll see the true power of the chain rule, which enables you to differentiate functions which you would otherwise not be able to differentiate. So to start with, let's just remind ourselves of how far we have gotten so far with differentiation. If we're given certain functions, then we are able to provide the derivatives. Now I'm going to write derivatives in the sort of longer notation of df by dx for this tutorial for clarity. Often as a shorthand we write f primed, but you'll see here with the chain rule it makes sense to be a little bit more specific, or explicit I should say, because that will make things clearer. And let me just list the derivatives that we have seen so far. So we have seen that if we have a function which is x to a power, let me just call that power p. So that could be an integer, it could be x squared, or it could be a fraction such as x to the power of 1/4, it can be any number. Then the derivative is found by bringing that power downstairs and multiplying it by x to the power of p minus 1. We've also seen that the derivative of the trigonometric functions sine x and cosine x are given respectively by cosine x and negative sine of x. And although you don't necessarily need to know this for higher mathematics, it's such a simple result that it is worth knowing at this stage of mathematics. We saw in the previous tutorial on calculus that if you have an exponential function with base a to the x, then the derivative is some constant that depends on the base times the exponential itself. Now we haven't seen what that constant is for general base, and actually with the chain rule we will be able to work that out. But most importantly, the case where the base is e, we know that this constant is 1, and we have the beautiful result that for the exponential function e to the x, the derivative is simply e to the x. Very pretty and beautiful. Now that's all fine, and these are sort of like building blocks to differentiate more complicated functions. But for example, say instead of sine x we had sine of 2x, or say instead of x to the p we had, for example, x squared plus 1 to the power of p. How would we go about differentiating those slightly more complicated functions? And that's where the chain rule comes to the fore. So what we're talking about here then are composite functions, and I will put a link in the description below the video to the earlier tutorials I gave on functions, and in particular composite functions. And this is where, instead of having the sort of simple expression f of x, a single mapping that takes us from x to our output variable, say y, we have something a bit more complicated. We have a function f of a function g of x. F of g of x. Now, I think in the earlier tutorial on composite functions I would have shown you this kind of figure. And let me do this because I think it will be helpful in getting a sense of this. If we just have a simple function y equals f of x, you can think of that I like to think of it as a machine. Okay, so you can think of functions as mappings between sets, and that's a very mathematical view. I like to think of functions in a sort of metaphorical way as machines with a big label on the box which says F, and then a sort of a chute going in and a chute coming out. And if we put something like X into this machine, it will spit out a number Y, which is the application of the machine to X. Y equals f of X. So what we can do is imagine bringing two such machines together. Let me draw this in black, I think. So let's imagine we have now, instead of a machine called F, we have a machine called G. Now, of course, I'm using the word machine just as a metaphor here. We're just thinking of some function G, and in goes a value X, and out of here comes the application of the machine to X. Oh, sorry, application of machine to X, which is G of X. But now we imagine that this goes into another machine. This is now the idea of the composite function. This one is called F. And now you see F is not accepting X, F is accepting G of X. And what comes out of this machine is that machine F applied to what was given to it, which is G of X. And we might call that output variable Y. Y equals f of G of X. So that's the idea of a composite function. Now at the same time though, we could just put a great big box around these machines. Okay? And you might not know what's going on inside this big box, and this big box might simply have the label H on it. So equally, we could say that Y is the application of this big machine H to the input variable X. In other words, we have a function H of X, which inside the green box is actually the application of a function F to a function of X. So I'm just really repeating here what we went over when we spoke about composite functions, but I'm using this sort of machine metaphor because I think personally it's one of the clearest ways to think about composite functions. So what we would like to do is work out the derivative of this function. We would like to work out dH by dx. So we can approach this in the following way. Remember the fundamental, not quite sure if you'd call it wouldn't really call it a law, the fundamental result of calculus given a function f of x is the statement that a change in the input variable x is related to a change in the output. So let's think about this top picture here. The change of the input variable is related to the change of the output f by a prefactor, as it were, which is what we call the derivative, df by dx. And this is strictly true in the limit that delta x goes to 0. So we have an infinitesimally small change in the input variable, and this gives us an infinitesimal change in the output, which is calculated as that change in the input times the derivative. And that's what we actually mean fundamentally by the derivative of the function. So we can actually now use this idea in the following way. If we think about the large box here, we have the simple statement that a change in h will be given by the derivative of the function h with respect to x times that change in the input variable. So we're wiggling the input variable, and out of this green box comes h of x, and we get a wiggle in the outcome of that, which would be effectively a wiggle in what we're calling y, which is just the numerical value of this function. But if we strip that green box away, then we see that we have two different machines inside. And so we can make the following statements. We can say, well, as far as that first box is concerned, a wiggle in x is going to cause a small change in the output of that first machine, and that's going to be related to the wiggle in x by the derivative dg by dx, because that's always the fundamental result of calculus. Small change in the input is related to a small change in the output by a factor of the derivative of the function. Likewise, for this second machine here, it's seeing a small change in g, and that will record then a small change in f. So we will have that a small change in the input to the second machine will give a small change in f, and it will be related by the derivative df by dg, because f just sees this input g. So we have these two statements, and so we can put those together and we will have the following. We will have that as far as the double machine is concerned, the composite machine, that change in the value of the output y, which is the change in this function f, is df by dg times the change in g, but then we can use this result to say that's df by dg times change in g is dg by dx times the change in x. And so you see we have two equations. This one looking at the larger green box telling us that the change in the output is the derivative of the composite function with respect to x times a change in the input. And then looking in more detail inside that green box at the two functions making up the composite function, we have that the change in the output is the derivative of the first function, or the outer function, sorry, with respect to what comes into it, g, times the derivative of that internal function g with respect to its input. So we can equate this derivative with this expression here, because they are the things that relate delta y to delta x. And so we have our fundamental result, which is the chain rule, which is that the derivative of a composite function, h is f of g of x, is given by the derivative of the outer function with respect to the inner function multiplied by the derivative of the inner function with respect to x. That is the chain rule. It is such a powerful and important result in calculus. Now, I don't actually have time or space to show you a simple example of this in this tutorial. As I said, I'm going to cover some examples in the next tutorial. So if you immediately join me for the second part of this discussion of the chain rule, we will show, first of all, a very simple example of this where you see that we can check that the chain rule actually works by being able to differentiate a composite function explicitly, and then by using the chain rule. And then we'll look at a set of examples where actually there is no other way with our current toolkit to differentiate those functions except with the chain rule. So I hope you've found this helpful. As you know, in these tutorials I don't like to just throw results down on the table. I think mathematics is a subject where you need to have both practical ability in exercising mathematics, but you also need to have a strong conceptual underpinning, because that will give you much more confidence in your understanding of the subject, and that's why I think it's worthwhile showing in detail here I would say a schematic derivation of the chain rule based on this fundamental result of calculus. So just to say this one more time, when you have a composite function h, which is a function f of a function g of x, the derivative of the composite function is the derivative of the outer function with respect to the inner multiplied by the derivative of the inner function with respect to x. And when I'm teaching privately, I sometimes liken this to having Russian dolls. You know, Russian dolls where you have a smaller doll inside a larger one, and inside that smaller doll is yet another smaller doll, and so on and so on. So here it's like you have a Russian doll of a Russian doll, and inside you have another Russian doll, which is your input variable. And the chain rule basically says that you successively differentiate by looking at the derivative of the sort of the outer shell of the dolls with the next one in, and then the derivative of that next one in with the one inside that. And so in fact, even if we had f of g, of I, of j, of k, of x, if we had many layers of composite functions here, the chain rule would simply multiply all those derivatives in a row, differentiating one function with respect to the one next in the chain, and that's actually why it's called the chain rule. Good, I hope that's been useful, and I'll see you for the next tutorial where we will do a set of examples. Thank you, and I'll see you next time.